All right, good morning, everybody. Thanks for joining us for this PVAnalysis webinar. First, kind of just want to, say thanks. I know it's tough to take some time out of your day and join us for a webinar, especially during these times. We hope everybody's safe and sound, everybody's families are safe. Second, just kind of a couple items just to mention here. As many of you guys and girls we are working remotely, hosting this webinar from our houses. So kind of just hang in there with us if somebody has a kind of a remote connection issue, or you hear a doorbell, or a baby or a dog in the background or something like that. Next, there is a chat window as we're presenting, me, Mike, and Brian. If you've got a question, just open up that chat window and ask the question. One of us will answer it as quickly as possible. Next, we're going to try to have a webinar probably about every week or every other week, so just be on the lookout on social media. We'll send out the email blast again for all you guys to join us. Last, just kind of want to thank Mike and Brian here. They're going to be the main presenters for the day. So thanks to you guys for taking the time and presenting PVAnalysis with us. Just do some quick introductions. My name is Dylan Abel. I've been at Winrock for about 8 years now, worked a few different positions from online systems engineer, doing installation and commissionings in the field, tech services manager, and now most recently I'm our product manager. Now I will hand it over to Mike for his introduction.
Hey guys, it's good to see you all again. I'm Mike Jones. I've been with Winrock for 15 years. This is my 15th year, and including the time that I spent mechanicking and doing analysis, it'd be 50 years in July. And I've used all kinds of analyzers and tested just about any kind of compressor agents you can think of. So I'm really excited to be able to help you guys while we're sitting at the house doing homework anyway. So this is really a nice venue. So I appreciate you guys coming and joining us.
Thanks, Mike. Now we'll hand it over to Brian here.
Yeah, here's Brian.
Hey, good morning, guys. Brian Blanchard out of New Orleans, Louisiana. Been in the industry for about 45 years. Been analyzing about 39. Good to have everybody here. Hopefully we can teach you a little bit something.
All right, awesome. Thanks, Brian. A little outline of what we'll kind of go through today. We'll go a little bit of just company background and our product portfolio, just kind of quickly here at the beginning. Then I'll hand it off to Mike and Brian, who will go through PV diagrams and curves, actual versus theoretical, some of the calculated parameters, and then fault diagnosis. Quickly here, Winrock is an Apergy company, which was formerly Dover Energy. You can see Apergy is made up of about 15 or so companies here that are well known throughout the oil and gas industry, from downhole monitoring, artificial lift, automation technologies. Winrock started off as part of CSI and then was bought out by 3 employees who then created Winrock. We've had 4 generations of the portable analyzer, starting with the 6300, and most recently we've got the 6400. Few different online monitoring systems. First generation was OnGuard, consisted of various modules for compressor or engine or vibration. We have our newest system, which is Platinum, and then we have our Auto Balance, which incorporates fuel valves on a slow speed integral to keep the balance in equilibrium. And then our newest product is Spotlight. We've got Spotlight for both compressors and high speed engines. We'll deep dive into each of these momentarily. So starting with Platinum here, it's really our Cadillac system. It's collecting data almost every second. It's got real-time data being displayed, and it also works with the Auto Balance for those integral engines. Moving down, we've got Spotlight. It's IoT-enabled system. It's really kind of a plug and play, easy to install system. We can go out on a compressor, on a 4-throw compressor, have it up and running in a few hours. Low cost system. You can see all your data remotely. We have a dashboard, which is called Windrock Enterprise, where you can see not only your entire fleet, but you can drill down into just one single machine. And then we have our 6400 portable analyzer, which you can go out and collect data on multiple machines. Our products are used, various assets. For the critical assets, those machines that really require the real-time monitoring, protection, you want to shut down at the sign of a catastrophic failure, or before a catastrophic failure, we recommend platinum. There's probably about 20% of the assets out there. And then for all those essential assets where you want to monitor the system, but you're not interested in the protection aspect, that's where Spotlight comes into play. So we can monitor an entire fleet and let you know when a problem may be occurring. And at this point, I'm going to make Mike the host. And he will get started on the PV analysis. Okay, Mike, you are now the host.
Close down my email. Sorry, guys. All right. Well, guys, I'll say again, it's just a real pleasure to have you join us for this thing here. And what we're going to be looking at is just the pressure versus volume card and what it entails, the calculations that we do from the PV. I know this is just one tiny piece of your analysis data that you bring in, but it's a real important piece. And this will just be the first of a series that we're going to be doing on these webinars. So here we go. And we got, PV diagrams. It doesn't make any difference what kind of compressor you've got. You've got an old slow speed integral, or you have a separable high speed. The PV diagram is the same for everything. So this is normally what the analyzer takes. It takes the pressure versus time, where you have pressure over here on. Let me turn on my pointer. Okay, we have pressure on this axis, degrees of crankshaft rotation on this axis down here, 0 to 360. So we can see the head end pressure trace in real time, the crank end pressure trace in real time. And from that, we actually create the pressure versus volume trace. Okay, now the pressure versus volume, instead of having crank angle 0 to 360 down here, we have 0 to 100% of the displaced volume or the swept volume, whatever you want to call it. And then this is actually just 1/2 of the revolution. So we go from 0 to 100% is zero to top dead center to bottom dead center. And from bottom dead center, we go back to top dead center again. So looking at that on the head end, then we can see in section A here where we re-expand gas down to where the suction valve opens up. Then we bring new suction gas in all the way to bottom dead center. Then the suction valve closes and we start compressing the gas in the C area here. We compress the gas up to discharge condition. Discharge valves open up, then we push the gas out of the cylinder. So that essentially is what the PV curve is. And there's the same thing on the crank end. While the head end's working like that, then when we go from top dead center to bottom dead center, then we're compressing gas on the crank end, discharging, re-expanding, and bringing in suction. Okay, doing just the opposite of what we're doing on the head end. Okay, now one of the main calculations that we get out of that is the horsepower. So your indicated horsepower. Okay, now all this area inside this PV diagram represents work. including these shaded areas. These shaded areas are actually power losses, but they're included in the horsepower. So all that area in there is work. So then if we look at the formula here, the horsepower is measured at the compressor piston face with an indicating device, which means your analyzer or whatever is your indicating device. We're taking a pressure reading and we're calculating the horsepower from it. It includes all your thermodynamic losses. Those are equal to the indicated horsepower minus the theoretical horsepower, or thermodynamic or compression efficiency equals the theoretical or gas horsepower divided by the compressor indicated horsepower. And then we've got our good old horsepower formula here. And this is kind of an antiquated one. And this is what everybody used to use, but we can see the PLAN divided by 33,000. So what that represents from that PV curve is the P is indicated mean effective pressure, and that's what we find out from the PV curve. The L is the stroke in feet, and it's in feet because we're dealing with foot-pounds of torque per minute down here at the bottom. Then we have area of the piston face, and then RPM, how fast is it running? Then we're going to divide that by 33,000 pounds per minute equals 1 horsepower. And that doesn't mean that poor horse has to pull 33,000 pounds in 1 minute. He could pull 33 pounds 1,000 feet in 1 minute. You know, it all works out the same. Now, in the old days, we'd take that PV curve there, which we got by various means, sometimes an old XY plotter or something like that hooked up to an analyzer. And we used a polar planimeter here. And with the planimeter, we actually measured the inside area of the PV in square inches and then converted that into indicated mean effective pressure. And that's just it. We'd anchor the thing, set the beam for the scale here, anchor it down here, and just trace all the trace of the PV in order to calculate the indicated mean effective pressure in there. Okay, now the way we're doing it nowadays, we have to have certain information to put in there. We need to have the connected rod length, and we need to have the radius of the stroke in order to calculate what the piston position is going to be at every degree of crankshaft rotation. Because as you can see, this is the speed of the piston. See, it's not the same. It's not the same for every degree of crankshaft rotation. It's speeding up, slowing down, speeding up, slowing down. And we can see right here with these bottoms and the top here, bottom dead center, we can see places where it flattens out there where we're not moving much per degree of crankshaft rotation. So the analyzer has to know that so that it can calculate every one of those how far that piston moved at every degree of crankshaft rotation. Because what we're actually doing, we're measuring force, which is the pressure times area. The analyzer can do that for us. So we know the area of the piston face, we know the pressure that's in there at every degree of crankshaft rotation. But what we have to figure out in order to calculate our horsepower is that we have to calculate work. And actually it's measured. So that's the force times the distance for the stroke, but it's at every degree of crankshaft rotation. So we have to know the distance that piston moved every degree so that we can calculate the horsepower on it. And then we can calculate power is work divided by time, which is the 33,000 foot-pounds of torque per minute. So once we get all that done, then it's pretty easy to calculate horsepower on it. It's just very dependent on your TDC setting. If your TDC is off, you're not going to be able to calculate horsepower correctly. Okay, now we talk about the suction volumetric efficiency. The suction volumetric efficiency is the percent of the cylinder's end displacement that the piston passes through if you draw an imaginary line from the toe pressure to the expansion line. Discharge volumetric efficiency is the percent of the cylinder's end displacement that the piston passes from the discharge toe imaginary line where it meets the compression line. Okay, so we have so what we do here, we go from toe pressure, you see on the discharge. Okay, we go from toe pressure, we draw that imaginary line right here till we meet the compression, then draw it straight down, and then we can calculate the volumetric efficiency. This is the actual percentage of the sweat volume that we use to move gas in this cylinder based on your clearances. Same thing on the suction here. We can calculate the volumetric efficiency from the suction by going from the suction toe, drawing our imaginary line all the way till we reach the expansion line, and then measuring that down here on our percent of sweat volume. So we used to have to do that with a Polaroid photograph and a ruler to figure out all these, and the oscilloscope screen had graticules on it to help us calculate what the volumetric efficiency was on it. Yeah, we're lucky now that that we can do all that with the computer. We just poke the button, we get horsepower. That's fun. Okay, same thing when we're looking at the crank end here. We draw the imaginary line from the toe on the suction to the expansion line, measure the volumetric efficiency at that point, and then we take the discharge volumetric efficiency from the toe to the compression line and do the same thing. Okay, and the reason we do that because we have to have the volumetric efficiency in order to actually calculate the throughput, or what is the capacity of the compressor is based on the volumetric efficiency. Well, actually, it's based on the displaced volume times the volumetric efficiency times RPM times 1440, which is a number of minutes in a day. Then we go through a pressure correction and a temperature correction divided by the compressibility factor. Okay, the pressure correction and the temperature correction is in order to turn it into standard cubic feet a day. What this does is whatever readings you took, it's correcting it back to sea level at 60 degrees Fahrenheit. So that gives you the 14.696 or whatever that's your sea level pressure, and then it's 60 degrees, and it's going to correct everything back to that so we can have standard cubic feet. But from the PV, the main thing we get from that is the volumetric efficiency. There again, your top dead center, and a lot of different things go into calculating your capacity. Other things that you may have to look at on that is of course your temperatures, your gas sample, and several other factors that go in there. The linearity of your pressure transducer, several different things in there. Okay. Okay, so one thing to remember when we're using your calculated capacity there is suction calculated capacity goes up with a suction valve or packing leak, or anytime you've got high pressure gas leaving the cylinder. The suction calculated capacity goes down with a discharge valve leak, or we have high pressure gas coming back into the cylinder. Discharge calculated capacity goes up with a discharge valve leak. Discharge calculated capacity goes down with a suction valve leak or a ring leak. Okay, just the opposite. Now what we're talking about here, the calculated capacities go up or down. Okay, the actual capacity is going to go down no matter what kind of leak you have. Okay, the average of the calculated suction discharge capacity goes up significantly with ring leakage, and generally up slightly for valve and packing leakage. Okay. But your actual is always goes down on that. Okay, here's things that's going to affect your capacity calculations. Here is a distorted PV due to an inaccurate top dead center, distorted PV due to channel resonance, toe pressure picks, volumetric efficiency, temperatures from the nozzle, gas properties, pressure zero offset, or pressure transducer linearity. These are just 8 of the things that may affect your capacity readings. And okay, now your flow balance is also calculated from those capacity readings that we use the PV for to obtain the volumetric efficiencies. So the flow balance is just telling you that it's the difference between your calculated suction flow rate and your calculated discharge flow rate. Okay, we get a result greater than 1, indicates that the gas leaking out of the cylinder into a low pressure area. And we have a result less than 1, indicates gas leaking into the cylinder from a high pressure area. If you think about it, that's really the only leakages that you've got. You've got gas coming in or you got gas going out. Those are the 2 leakage patterns that you can have. Okay, your accurate flow balance is dependent on the accuracy of the TDC reference. There we go again. That's probably the most important thing that you want to make sure is correct on your on your PV card is the TDC reference. The toe pressures, suction and discharge temperatures at the valve ports, gas compressibility, and volumetric efficiency picks. And go into stress that flow balance itself is not a reliable way to determine the health of the compressor cylinder. And you never want to adjust the TDC based on that. Okay. Okay. Another thing that we're looking at when we're calculating capacity is the Z factor of the compressibility, and it's also known as the. I'm about to move this out of the way. Yeah, there we go. It's the ratio of the molar volume of gas to the molar volume of ideal gas at the same temperature and pressure. It's a useful thermodynamic property and whatever. Actually, what the Z factor is a fudge factor. It's saying that the gas sample that you're compressing has these characteristics that don't really match up with the ideal gas law. So they're saying we're gonna modify that a little bit to make it where it does match up. And you're talking about molar volume of ideal gas. This is where this comes from. It's just the amount of any substance that has the same number of molecules as 12 grams of carbon 12. Okay, and so going by that criteria, a mole of methane is 379.48 cubic inches at sea level and 60 degrees Fahrenheit. So that'll kind of give you an idea. When we're talking about moles, that's what it is. And here's the ideal basic gas law. It's saying the pressures, the volumes, the temperature should match up from suction conditions to discharge conditions. Okay, if it doesn't, that means the equation is not balanced. It means there's leakage or there's temperature entering or leaving the process, which there's always temperature entering and leaving the process. But with a compressor cylinder, when we're looking at that, the turnaround is so quick when we compress gas, expand it, compress it, expand it, that the temperature entering or leaving the process doesn't really play into the calculations at all. It happens too quick. Okay, now here's another example here where we've got the Z, or the compressibility factor on the discharge side. We've got a compressibility factor on the suction side, and this is Z standard on that report is what the compressibility would have been had that gas mixture met the perfect gas law, but it hasn't. So we have to fudge it a little bit to make it work out. Actually, what they say is this tells you the compressibility of the gas under field conditions rather than laboratory conditions is what it amounts to. And we got a couple of equation of state is what we call that, where we calculate the suction and discharge compressibilities, and these are just some of the different ways we do it. We use the Benedict-Webb ribbon. I think 1987 was the last update on that. That's the one we use. And if it won't match up on that, then it goes all the way back to the Redwood-Kwong, which is a very simple one. So we have like 3 different ones. We'll use the Beatty-Bridgman is another one that we use. So we have like 3 different equations of state in there. Uses the most modern. If it can't do a calculation at that, then it'll just keep scooting back to the Redwood-Kwong, which actually anybody can make a equation of state out of that. Okay, now here's a cylinder end plot. What we do, we plot it on a logarithmic scale. This is your log P versus log V, which is logarithmic pressure versus logarithmic volume. So this is actually a pressure versus volume trace. Okay, for that, we need to take the cylinder end pressure and need accurate cylinder end clearances. That is very important. We have to have an accurate gas analysis. It calculates the end value of the gas, which is a polytropic calculation. And what it's doing is predicting the compression line and the expansion line in order to line those things up where they can be parallel to each other. So if they're parallel to each other, then you're looking at a normal cylinder there. And the way that does that, if you can see, okay, from this toe pressure here up to the volume here, we have what they call a run. Okay, then we measure this toe pressure down to this scale on the volume, and that's the run there. So we're comparing the compression line with the expansion line. So we got a 1.55, a 1.58 with an end ratio of 0.98, and that kind of correlates to your flow balance, except it's done differently. We use the end value quite a bit on when we have high compression ratio, low throughput cylinders. Your volumetric efficiency picks could be kind of iffy on that type of situation. And we found out that the end ratio, as long as we have the right clearance volumes in there, it works better in that situation. Here's one. The end compression and expansion values are derived from the actual slopes of the collected indicator card. Okay, in log. Now, you'll also notice that when we're in log here, this is the only plot that the analyzer puts out that's actually in PSIA, or absolute pressures. Okay, we already did that. So this is where we can pull up the clearances, and we can see the calculated suction, the calculated discharge clearances, and those should be pretty close to each other on a healthy cylinder. And the one we want to use is the average calculated clearances on there, so that we can draw a really good PV card. And if you think about it, if you've got some leakage and these are going to be off, the calculated suction, calculated discharge will be different from each other, but the average is average. So it'll still give you a fairly accurate look at your log. Okay, you're calculating your cylinder end clearances. Thank goodness the analyzer does that for us, but we've got two different methods. We've got the GPSA model, or a method, and it uses out of the GPSA engineering handbook, uses that formula, and that formula is actually modified by the compressibility factor. Okay, so some gases that doesn't work real well, so we have a modified Southwest Research method, 8410A, which uses their formula, and then it's modified by the ratio of specific heats, or the K value. So here again, we've got some things going on here that yeah, the GPSA works better for adiabatic compression, such as occurs in most natural gas compressors, and the 8410 method works better for unusual cases where and this is the kicker here, the gas mixture's compressibility changes significantly from the suction to discharge. Like when you hit up around supercritical on CO2 or something like that, then the 8410 will actually work better than the GPSA. And it's actually pretty easy to tell. You just switch back and forth between them and use the one that gives you the best calculations. There's no real big rule of thumb there. And this is kind of what we're looking at here on these end values here. After we get the correct clearances and everything in there, and we've got a healthy cylinder, so we've got the polytropic calculation, and these are from the slope of the lines. So we're looking at the expansion and the compression, and those should match up fairly close to what your K value is. Okay, and then here's a list of things that we can tell from the log P versus log V. Is leaking rings, the compression and or expansion events do not follow straight lines, and this is true with just about any kind of leakage you've got going on there. In there, they will not follow straight lines. The slope of the compression line decreases, slope of the expansion line increases, and the end ratio increases. Okay, leaking suction valves, the end ratio increases. Leaking discharge valves, the end ratio decreases. Okay, in a packing leak, it will look just like a suction leakage. Something else that we calculate from the pressure versus volume card is losses. Now they call this on reports power valve losses, but it's really not valve loss. It's actually the total power loss in these shaded areas here from the piston face all the way out to where the gas leaves the yard. So the only way that we can tell if that's actually a valve loss is to pull some overlays. Like this black overlay here is following so close. That's one that's taken right out of a valve cap. See? So that's telling us this little area right in here is all the loss we have on those valves. And this second trace we've got here is out of the nozzle. And we can see that what restriction that we've got in there, or that we have this much loss between the nozzle and the piston face. So it's telling us that our restriction is not in the valve so much as it is from the nozzle. You go through the flange, the cavity, and the valve. So that would be a accumulation of all of those. I think Brian's taking care of those guys that are raising their hand, aren't you?
I am, Mike.
You're the man. All right. Okay, excessive valve loss, passage loss indicating from a 10% rule of thumb. Actually, for valve losses on a slow speed integral, we would like to see, right straight out of the factory, brand new unit, we would like to see 3% or less. High speed units, the rule of thumb on that is actually 12%, about 12 to 15, because I see them 17 to 24% all the time, and that's about the best you can get off some of those high-speed units. And it's all dependent on the valve lift and flow area, the spring tension, form material, PT and PV curves appears rounded during the suction or discharge phase. Verify with nozzle pressure as close as possible to the valve. And that's the kicker right there. In order to tell whether we've got valve loss or we've got restrictions in the line downstream of the valves or upstream of the valves, we have to have these nozzle traces in order to figure that out. Then we got flow area of nozzle, orifice, bottle, piping, or cooler is insufficient. Unwanted bottle or pipe pulsation. We got clogged suction screens, collapsed bottle baffles. Verify with nozzle pressures throughout the piping system. So you may find out that your cooler out there has had too many coils plugged, and that's what's causing your restriction. Okay, and these are on your report. These are your valve losses that's calculated from that, and these losses are actually a percent of valve loss. Like on the discharge here, this is 13.3% of the indicated horsepower. Is what we're looking at here. So, and you add the discharge and the suction together to get your total loss, and that's what would have to fall into the criteria of 3 to 4%. Total loss, or 12 to 15% total loss, is adding those two together. Okay, let's look at some of the leakage characteristics of the PV curve. And when we compare those to theoretical, the leaks really show up. Okay, so the main things you can take away from this is a leakage can only occur from a high pressure to a low pressure. It's like, water flows downhill. And a valve only leaks when it's closed. An open valve doesn't leak. Okay, then here we got the various kinds of leakage that you can have. We can have high pressure going out of the cylinder, high pressure going into the cylinder, internal leakage where the gas is moving back and forth across the piston rings, or some external leak, going across the packing or out of flange or something like that. So those are the types of leakage that we can have. Okay, if we look at this is a unsmooth one, but you can see where our theoreticals clamp down pretty close to the toe, to the area in the toe pressure. We've got a little bulging going on in there, but that's really insignificant on this type of cylinder, as long as everything matches up. Okay, now if we pull one up, a pressure versus volume trace against the theoretical, we can we can really see suction leakage going on here. And we can see that because we have a greater volumetric efficiency. Remember, our throughput is calculated from the volumetric efficiency. So when we overcalculate volumetric efficiency, that means we're recycling gas in the suction, and we're starving the discharge. See, so that's a suction leakage. Whichever one has the greater VE over what the theoretical would be. And there again, these theoreticals are real dependent on your gas samples you've got in there and your clearance volumes. So we want to make sure that those are all correct. And this is a very useful tool. This is one of the most useful tools that you have in your kit. Okay, and this one here, we can see discharge leakage. See, the volumetric efficiency of the discharge is way more than what the theoretical says it should be. So that means we're recirculating gas in the discharge system, and we're starving the suction. So we can see we have a fairly good discharge leakage going on there. Okay, then the good old ring leakage, which everybody has a hard time finding, but against the theoretical, if you can pull that theoretical up, it really is easy to tell because we've got this big bulbous nose here on the toe, and you can see where it deviates away from the theoretical until we hit pressure reversal. Okay, when the pressure reversal, the pressure starts getting higher on the other side of the piston, that we have gas leaking the other direction. Then it starts moving its way back to the theoretical. It almost gets there before we reach discharge conditions. But on the head end, we can see the same thing happening, and it actually crosses over before it gets to discharge conditions. So this is your classic ring leakage pattern here. You can even see that without the theoretical, but when you throw that theoretical on there, it really makes a big difference on being able to diagnose it. And that's about all I got, guys. How long did we go? What you think, guys?
About
What do you think,
about
Brian?
37 minutes. I'm still answering some questions
Now we
here.
can take some questions.
Yeah, I'd say at this
Got
point,
any that I can.
we can just read some of those questions out loud, Brian, and then tag team answering them. We got about 20 minutes or so.
Yeah, one question was, when would you use in ratio over flow balance, Mike?
Okay, well, really when you have a high compression ratio and a low throughput, that would be a tall, skinny PV. Okay, you're talking about when you have a tall, skinny PV like that, it's very easy for the volumetric efficiency measurement to be off. Okay, if the volumetric efficiency is off, then that is going to affect your flow balance, of course. But if we're just measuring the slope of the line on the compression and the expansion on that long, tall PV, it'll be a lot more accurate than the flow balance because it's not depending on the volumetric efficiencies to make the calculation.
Okay. So how does horsepower affect amp draw on a motor-driven compressor? How does horsepower loss affect amp draw?
Yeah, 1.341 kilowatts to the horsepower. So if you're overloading the amp draw on that electric motor, then you will see it, on the amps. Amps are going to go up if you're overloading.
Yeah, I think he's talking more about valve loss if you have excessive restrictions.
Oh yeah. Okay. Well, if your motor amps are high and your throughput is not affected, I mean, you're doing a normal throughput, then those valve losses will cause quite a bit more motor amp draw. Because like I said, I've seen some of those that are using that the total valve losses are 20%. Well, that means you're going to add 20% more amp draw to that motor than you would if the losses were a lot lower. That'd have a big effect on it.
Why is the valve loss greater in a high-speed compressor compared to a slow speed?
Well, just because of the dynamics of the speed where everything's taking place. You know what I'm saying? It's moving that gas faster through there, so the losses are going to be greater than what they are on a slow speed because I mean, the difference between 250, 300 RPM moving that gas and 1400 RPM, the dynamics is quite different. Plus those little high-speed units, they have smaller piping, smaller bottles, smaller coolers, you know, everything that relates to all that different restriction that you get in there.
Right.
Faster, you know, that's.
Yeah, the piston speed is faster.
Yeah.
Did you explain leak index?
Could
you pull up a PV card here and kind of explain leak index?
No, I didn't. Okay. Let me see if I can get out of this here. Okay. Okay, what we got here? Yeah, we'll just pull this one up right here. Okay, if we look at this card right here, and we're looking at the PVs. Okay, and we turn on and these are tall, skinny ones. So we turn on the leak index, and it's seeing suction leakage or slight ring leak. Okay, so what the leak index is actually doing, it's coming a designated percentage lower than the discharge toe point, and a set parameter higher than the suction toe pressure, so that your toe pressures and volumetric efficiencies don't play into it. So what the leak index does, it does about a dozen calculations back and forth across that PV, and during those, we're talking about capacity calculations. So during those dozen calculations or so, or however many it is, if it sees high pressure gas leaving the cylinder, then during those dozen calculations, then we can call that a suction leak. If it sees high pressure gas entering the cylinder during those dozen calculations, then we can call it a discharge leak. Then if we see high pressure gas leaving the cylinder for a portion of the stroke and then re-entering, then we can call ring leak. So, you know, so it can be very good. The thing about it is, though, it needs to be tweaked for the type of cylinder that you're running. Like here, if we got a high compression ratio and we have a low throughput, then we can go to our setup in here in the software options, and we can go to leak index here, and we can actually tweak those as far as the sensitivity, either higher or lower, because the high skinny PVs here are going to be a lot more sensitive to leakages, and the low squatty ones, I call them, the low differential high throughput cylinders are very insensitive to leakages. So you need to increase the sensitivity on the low ratios and decrease the sensitivity on the, did I do that right? No, decrease the sensitivity on the low ratio, increase the sensitivity on the high ones. You got anything to add to that, Brian?
Yep, that's good. Can we tell leakage based on the suction VEs and the suction and discharge toe pressures?
I'm not sure I understand what we're talking about there.
I guess he's wanting to look at the VEs and the suction and discharge toe pressures to try to tell leakage, which is fine. That you can do that in a way, but we have better tools than that. We have flow balance, leak index, and of course in ratio, where we can tell valve leakage. So the computer's going to look at these. Yeah, the computer will look at these toe pressures and VEs, and then it'll calculate leakage by the flow balance and the in ratio and the leak index for us. So we don't really have to do that. How about
you just have to make sure that the data you're bringing in is correct. That's the.
Yeah, so that goes into our next question. Can you show how to verify top dead center with a PV diagram.
With a PV diagram? Oh.
I mean, if your flow
Well,
balances it off.
if I know my my volume, if I know my clearances are right and my theoretical is going to be right, you can verify it by looking at your PV to your to your theoretical there, and you can actually move your top dead center till, as long as you're in a healthy cylinder, you can move it to match your theoreticals to get real close to your TDC. Then we have other ways of doing it besides that. That might be a whole nother class.
Do you want to pull up your MD software again and kind of pull up your clearance and your flow balance chart and kind of move it?
Yeah,
let everybody see how we do that.
Let me find a different thing here. Okay, we got, let me find one here. Here we go. Okay. So let's look at this right here. Okay, this is a very healthy cylinder. So this is what you'd want to start with if you're going to be manipulating your top dead center. So what we want to do now, we want to look at our leak index, and mainly we want to see the flow balance, and we want to see the clearance calculations there. Next thing we want to look at is pull up our clearances. I'll put it down here because this gets kind of busy before we get done. And then we want to go into the modify remove line. Okay, now if you look at these calculated suction, calculated discharge on our clearances, this is in a healthy cylinder to get, when we get the right top dead center, these will be very close to each other. Okay, we can go right down here to the modify the day offset. And let's move it, say 3 degrees forward, which would be to the right. Get the update, you can see, okay, you can see our flow balances went out on us. We can, if we had the full report up, you can see your horsepower percentage of your rated load would be moving on you too. But the main thing is here on these high-speed units, the calculated suction and calculated discharge, they're getting further away from each other. See, when I do that. Okay, so let's say yeah. Okay, so let's go the other direction. Oh, excuse me. Okay, let's go the other direction, 3 degrees. So we're going to the left 3 degrees now. So we click that, and we'll see that your calculated suction, your calculated discharge, they flip-flopped on you now. So now the calculated suction is higher than the calculated discharge. Okay, and if we want to zero in on that, see, we can move it just a couple of degrees at a time. Watch those numbers. Now you see how close they're getting to each other again. Our flow balances are perfect there, 1 and 1, because we know the cylinder's healthy. Okay, so we're going to go another half a degree, and you'll be able to see here how much difference a half a degree makes. So this is your clearances are very, very sensitive to that top dead center. So we'll move it back to 0. And we're back to about as close as we can get on it. Oh, we might go half a degree more on that. Yeah, look at there, half a degree on it, and even got better. Now you see your flow balance is 1.01, 1.01, but that's normal. That's pretty much normal on high-speed units. So if you'll use that method, which I taught all of our spotlight people how to do this, and they're very good at it now. So we get data in on that spotlight there, and they've got that TDC nailed down. So I hope, did that help?
That does help, Mike. Staying on this subject here, do you have any advice on adjusting the VE toe pressures, or what drives the decision to adjust them all? So we do have the
Well, when
capability
you
of
pull
adjusting
up,
the toe and the VE on a PV card. So if you go to the PV card,
oh
you
yeah,
might,
oh
so
yeah.
why
Well,
would
you
you
see
adjust
these, we
it?
can. Well, we get some every once in a while, and I'd have to dig for it, but I've got some in there. We're looking at okay, where our toe picks are. Okay, you see this where that's lining up, where that was lining up, those little dots. Those are perfect. That's where exactly where they're supposed to be. Sometimes we get a really wild spike up here on this end. It's going to pick the toe up here, and we can visually see that volumetric efficiency pick is not going to be good. So you can actually grab that, and you can move it down to where it should be, or you can use the little spinner boxes up there to move it. But it's if you look at it, and if you got a high area in here that's causing it to be off, or sometimes on the suction side down here, we get a loop in the pressure, like right here. It will extend higher than that, and it will actually pick that as the expansion line. So that blue dot that we're seeing there will actually show up right here in this area, and your calculations will be off and everything nutty looking. So we can actually take that and move it all the way down here. What we don't want to do is disrupt the integrity of where our toe pick is, if the toe pick is correct. So if we did move this one, say down here like this, we would want to make sure that if we moved it out here to where it met the expansion line, that we kept the integrity of the toe pressure as best we can. Does that make sense?
Yeah, and I guess that kind of answers the other question that was asked. Can you discuss the loop over seen at the toe on some traces?
Yeah, it's a pulsation going on in there. You know, if you can't smooth it out, then you're going to have to move the toe pressure to take care of it.
Another question is,
Yeah,
how can I see?
some of those get a big loop. Here, let me turn that off. See now this one here would have it, if I didn't have it smooth enough, I'd have a loop here and I'd have a loop down here, one way up here. See, so you know, make sure you put enough smoothing passes in there to take care of it.
Maybe you could show how we use the smoothing function here. If you turn it back on and then go up and down until we get the yellow.
Yeah, there's actually several different ways of doing it, but we can go into that. Okay, like this one here, I got it 14. That's probably a bit much, but okay, we'll enable the smoothing. Yeah, this is pretty high speed, so we can click this to increase the smoothing passes on it. Like Brian said, you hit the yellow, and then you back off one. Is the way most people do it, and that's still very good. That's a good one there. Most aerial compressors, because most aerial compressors, because of the dynamics of the tube, the valves, kidney valves, and everything else on it, about 12 passes is what you need for 1200 RPM. 1000 RPM or so, you may only use 10 passes, because a lot of that's dependent on the RPM too.
Yeah, I mean, basically, I think we're trying to smooth it to where we get our toe pressure to match our actual gauge pressure or bottle pressure.
Yeah, you know, pretty close. We just want to make sure that we don't have any interference on that pick, you know.
Right. So, and how about the leak index? Do we add smoothing to the leak index?
Yeah, we can. We can actually add a different one to that than you use for your normal smoothing. We can go up to the software options, our leak index, and right here we can, where is it? Did we lose that feature in our new software? Okie dokie. Yeah, I think it's now using whatever you put in there.
So it was 11.
Yeah, so it's using 11 there. Let me yeah, this is brand new beta software, so we'll pull up the other one. Okay, now we'll go set up software options, leak index, and then here we can put in a smoothing factor separate from the one that we're using. This is the current this is the current version of the software. So we'll have to find out from the software people what we're using now with the newer model, the beta that we have. I'm sure it's probably using the general one that we put in for regular smoothing instead of having a separate one for it.
Okay.
Yeah, no, that smoothing is real important for rod load and, you know, leak index. So.
Okay. I think we have a time for maybe 1 or 2 more questions. I see it's 10:57 right now.
Okay.
I got a question. Somebody's wanting to know if the pressure curve changes dependent on the type of valve, plate or poppet.
Oh yeah. Yeah, the pressure will change because some of them you'll have a lot higher differential pressure to get the valve open. And some of them will have more losses, I have less losses, you know, it just depends on where you go with your valve. Get some really highly efficient valves out there, and you've got some that are not so efficient, but they last a long time. So it just depends on what you're concerned with, efficiency or being able to stay home on the weekend. But yeah, your valves will make a big difference.
Okay. Okay.
Hey, Mike and Brian, sorry to interrupt here. We're getting close to our time limit here. We you know, had the webinar set up for 1 hour, just so it doesn't cut everybody off. We just want to say thanks to everybody for attending. And if you have further questions, just reach out to us. You can contact us through the website. We will also be sending out this webinar. We're going to just clean up the little practice session we had at the beginning, and then we'll get it posted on social media and sent out to the email blast. Thanks for joining us, and everybody have a great day. And thanks to Mike and Brian for presenting.
Hey, Dylan,